Right. So I think many of you have gotten my email about the midterm exam booklets being available out in the hall here. If you haven't found it already, it's in this corridor right outside 201, 203, in literature racks on the walls by last name. And I encourage you to get your exam, look at it, look at what questions you got right, got wrong, and learn from it. So I reuse questions on later exams, including the first midterm is fair game. So you will see questions you have literally seen before. All right. Well, so where I am with material is flashlights, even though I haven't brought a real flashlight here. I'm sort of violating my rule of trying to talk about real stuff. So we got deconstructed flashlights. And if I can convey to you this hour, really all of what electricity is doing inside a deconstructed flashlight, you know, it's sort of probably one of the most useful parts of the class. We'll get further into electric power distribution down the road, pretty near future. So how power is coming from the electric company to here, but the heart of it is just right here on the table. So that when I close this switch, the light bulb goes on. So I will do my best to convey all that understanding to you. So where I left off, and then sort of to reset the stage, we've got a source of electric power, which in this case is a car battery, and we have a consumer of electric power, which in this case is an old-fashioned light bulb, a light bulb with a filament in it that gets hot and emits heat because of its temperature. So it's called an incandescent light bulb. That's the name for that phenomenon where a hot object actually emits light. And everything else is just supporting hardware for this. And of course, there's a switch. So, what is sort of going on the level of physics? Well, first off, when the system is running, it's a circuit, literally a circuit for electric charge. And again, by electric charge, I'm referring to positive charge. Later today, I'll come back to looking microscopically at what's moving and the complications as a result. So, but it's charge moving around this circuit, and the point is that the light bulb doesn't want to accumulate charge. It wants to accumulate energy. If it tried to accumulate charge, the charge, it all being like charge, all positive charge, it would build up, and you'd have a whole lot of positive charge. That positive charge would begin to repel any further positive charge. Two ways to look at it. Basically, there would just be electrostatic repulsion of the newly arriving positive charge, and it would be repelled. I can make political statements about trying to keep out immigrants, but I won't. I didn't say anything. So the light bulb can't keep the positive charge. Bad things will happen. So it takes the energy out of the positive charge and returns the positive charge to do the circuit again and again and again and again. And this is a general theme of electric power distribution. It always involves at least two wires. One to bring in electric charge with lots of energy, and one to return it with less energy. Because the energy charge is measured in terms of voltage. The charge arrives at the light bulb at a high-ish voltage. It's not very high, it's about 11 volts. And it leaves the light bulb's filament at a low voltage, getting close to zero, but not quite there. So in a general theme, charge going from high voltage to low voltage gives up energy. And so in this case, it lights the light bulb. Charge going from low voltage to high voltage, the direction it does not normally go, it doesn't do it spontaneously, that is, then it's picking up energy. It's evidently going through some sort of power source, something that's adding energy to it. In this case, the battery does that. So to just put some details into this whole idea. First off, what's the charge that's going around the circuit? We measure charge in units, and the standard unit of charge is the coulomb. And what is a coulomb? It turns out that the modern definition of a coulomb is it's a specific number of elementary positive charges. as I said way back, the subatomic particles in our world, some of them actually just simply come with charge on them. It's just a characteristic of our universe, that every time you have a proton in front of you, you also have one fundamental unit of positive electric charge. Protons always come with that amount of charge, and it's precisely the same on every single proton, for very fundamental reasons. It's the same to all decimal digits. It's truly exactly the same. Electrons, in fact, come with one fundamental unit of negative charge. Awkwardly true, but it's true. And anyway, the Coulomb is a specific number of the fundamental positive charges. That number is about 6 times 10 to the 18. So it's a whole boatload of positive protons altogether. But that's our unit of electric charge. And what's happening is electric charge is flowing around this circuit, and if we stand and watch at one point in space, say like in this wire, we watch the charges go by, we might say that and sort of tick off the fundamental charges going by, and we eventually figure out how many coulombs are going by. We do care about the rate at which charge is flowing by per unit of time, something we would measure in coulombs per second. How many coulombs of charge are going by every second in a wire? And that is a physical quantity. So the physical quantity that we're starting with is charge. And its official units are coulombs. The quantity that I'm now trying to convey to you is the flow of charge, the current of charge. So charge going by, how much goes by per second? And that physical quantity is called current, not surprisingly. Electric current, if you want to be more specific. And the unit that we use for measuring current is the coulomb per second, but it's got its own name because it's so common. It's called the ampere or amp. So this is something you almost certainly have encountered from time to time. Amps or amperes. That's what an ampere is. It's 1 coulomb per second going by. So if we watch the flow of charge in this circuit, I happen to know that the amount of current going by based on this light bulb, which is, I think, let me just double check. Yeah. It's about 7 amperes. So when I turn this on, if I watch and count the coulombs as they go by, it's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. There are about 7 of them going by per second, 7 amperes. You okay with that? Well, knowing that and knowing the characteristics of the light bulb, we know a lot. We can know a lot about the circuit. Here. Let me add more details. This battery is a 12-volt battery, meaning that it takes in charge at 1 voltage, and it delivers charge out of it takes it into the so-called negative end. It delivers that same charge moments later at the positive end, having given that charge 12 joules per coulomb of extra energy. That is a 12-volt increase in the voltage. So every coulomb that goes through here picks up 12 joules of energy. Well, if there are 7 coulombs going around the circuit every second, 7 amperes, and every coulomb picks up 12 joules of energy, then that's 7 coulombs per second times 12 joules per coulomb. That is, what's 7 times 12 is 84. That's 84 joules per second that the battery is adding to charge as it goes by. You okay with that so far? I know I'm doing numbers in thin air, and that's always a challenge, but you simply multiply the number of charges that go by per second times how much energy is given to each charge. And they're picking up 84 joules every second. Well, 84 joules every second is a measure of power. And the joule per second is known as the watt. So that's 84 watts. So this battery is giving 84 watts to the passing flow of current. And the light bulb is consuming pretty much that 84 watts of electric power. So a source of electric power, like a battery, how much electric power does it provide? You take the voltage rise in that battery, and I call it voltage rise because the charge enters at low voltage and exits at high voltage, having been lifted up in voltage. It's almost like lifting up stuff in altitude, packing it full of, if it were truly in altitude, it would be packed full of gravitational potential energy. This is not, it's being picked up in voltage. It's being given electrostatic potential energy. So the voltage rise in the battery, voltage rise tells you how much energy every coulomb's getting. And if you know also how many coulombs are going through the battery and being given this rise, you can multiply the two together to get the power the battery is providing. So just as a general rule, the power provided by an electric power source, whether it's the power company or whether it's your battery, is the product of the voltage rise in the battery times the current going through the battery. Is that okay? The power provided by the battery is the product of just two things. The voltage rise in the battery times the current going through the battery. And I want to make sure it's clear. The voltage rise of the battery says how much every passing coulomb gets. And the current says how many coulombs pass per second. So the product of the two is not very complicated. It's just the energy grand total. The charges are essentially the carriers. They're the delivery people doing the loop. The battery is just giving a certain amount of energy to the team. All right? The light bulb is the consumer. I'll come back to the wires in a moment again. The light bulb is the consumer of electric power. It receives charge at high voltage and wipes out its energy and lets it out at low voltage, having stolen all the energy from the passing charge. And the power that it receives is the product of the voltage drop in it, because the voltage goes down as the charge goes through, times the current going through it. So they're just sort of mirror images of each other. The battery adds energy to every passing charge. The light bulb consumes, removes energy from every passing charge. And that arrangement where the current times the voltage rise or the voltage drop, it survives into the world of electric power delivery in general. We'll see why the surviving is kind of miraculous. Electric power distribution is not battery-like. It's got this bizarre twist to it that the voltage is not constant in a power outlet. But nonetheless, it turns out that if you look at suppose you plug in a heater, or a hair dryer, even more familiar, a hair dryer, and it's an 1,800 watt hair dryer. That's pretty typical. 1,800 watt. Where does all that energy, the power, show up? That's 1,800 joules every second. That's what 1,800 watts means. How does it show up? Well, it's going to show up in the form of a 120 volt voltage drop. And this is a little oversimplified because of the weirdness of our power distribution system. But you can imagine that the current shows up at 120 volts, goes through the hairdryer, and leaves at 0 volts, having lost that 120 joules for every coulomb that made the trip. Okay? Well, how many coulombs are going by every second in order to deliver 1,800 watts? I mean, I could do this as a question, but I'm not prepared to do it, so I'll just tell you. It's about 15 amperes. You need about 15 coulombs every second, each coulomb dropping off 120 joules to get to 1,800 watts. And so that's the current flowing in your hair dryer, about 15 amperes. Is that okay? That happens to be the most that you're supposed to be able to get out of a conventional electric outlet. The outlets in this room are 20 amp outlets. Most people's household circuits are 15 amp circuits. That 15 amps is enough. If you draw more than that out of the circuits, you begin to have to deal with the fact that the wires are also consumers of electric power. Okay, but let me just make sure we're okay so far. If you're got an 18 watt, 100 watt hair dryer going, there's about 15 amps going through the circuit. It's dropping off 120, is going through a voltage drop of 120 volts in your hair dryer. Something is taking it the other direction from low voltage to high voltage and adding 120 joules per second. What's the something? It's probably the electric company, which we'll deal with down the road. It could be a generator in your backyard if you just happen to be off the grid. But that's the idea. Okay? It could be a whole bunch of car batteries. All right. About this circuit, so why is the current in this one, remember, coming back to this, where the current I said is about 7 amperes. What determined that? Why isn't it 3 amperes or 1,000 amperes? Who made the choice? And it turns out that it's the light bulb's choice. What the light bulb is a bad conductor. It's pretty much a normal electrical conductor, but just not a good one. And what is not a good one? Well, all of these conductors, basically every conductor with one critical exception that I will try to remember to say something about, they're all consumers of electric power. They do not carry electric current for free. Electric charge does not coast through them, according to Newton's first law. It tries, but it basically experiences friction-like effects in going through. It bumps into stuff on its way through the wire or any other conductor. And so you have to push. And the push comes about by way of a voltage drop in the wire. The current enters the wire at 1 voltage and it leaves at a slightly lower voltage. Having used that drop in voltage to create an electric field, because again, a gradient in voltage is an electric field. So there's a push. You can think of it, if you want to think more physically in terms of charge, there is more positive charge on the wire at its entry than there is at the exit. And so there's a little bit of a repulsion of positive charge that wins, pushing the passing charge forward in the wire to keep it going. So these wires are all demanding a little bit of a voltage drop to carry any current at all. The light bulb is the dominant participant in this. It wants a big voltage drop to carry current. And at about a 12 volt voltage drop, which is all we've got to work with here, because that's all the battery will provide, and I'll talk about that in a minute. That wire in that light bulb will carry about 7 amperes. If you wanted to carry more current, which would probably be a bad idea for the light bulb, you'd have to push harder, and you would have to use a larger voltage drop across it. And it turns out that most of these conductors, very widely around the world, things that conduct electricity, will carry current from the high voltage end to the low voltage end in proportion to the voltage drop. That is, if you use 12 volts to push current through that light bulb filament, a certain current will go through. In this case, it happens to be 7 amperes. If you double the voltage drop in the filament, in that wire, so that you're pushing twice as hard, the electric field's doubled, the current that goes through the filament will double. It didn't have to be that way. It turns out that it is that way, which is kind of neat. Makes life very simple. If you take most conductors and you measure how much current goes through them when you got 1 volt of voltage drop, you can predict how much current will go through at 2 volts voltage drop, or 10, or 0.01. And that result, where most conductors carry current in direct proportion to the voltage drop across them, it's known as Ohm's Law. So it's named actually after a high school teacher who figured this out a long time ago, Ohm. I think Gregor Ohm, I forget his first name. Anyway, it's almost ubiquitous. In the era of electronics, there are a lot of cases that violate it, but most things live by it. And so this filament was actually constructed with just the right characteristics so that at 12 volts, it will carry 7 amperes and get just hot enough to emit its brightest light without having a short lifetime. If I use 2 batteries and I expose that light bulb filament to 24 volts voltage drop instead of 12, the filament would briefly say, great, you're pushing harder. Instead of 7 amps, I'll take 14 amps. It would overheat, and that would be the end of the light bulb. It would be gone in a jiffy. And so in the era of incandescent light bulbs, they would adjust, they would make the filament just right, that it gets just the right heat for when powered by a certain source of electric power with a certain voltage rise. What I've got here, I'll put it back there, I just want to wave my hands with it. This is another deconstructed flashlight, and I can show you it works. If I plug it in properly. Okay, so it's just a simple circuit, same idea. It's made with 3 D batteries, alkaline D batteries, which again remain somewhat familiar to you all. All this stuff is in flux and changing. But so we've got 3 alkaline batteries. They together, each one individually, provides a voltage rise of 1.5 volts. And they're working as a team. So that charge is arriving here at let's say 0 volts, entering here. This first battery adds 1.5 volts to it. It does some work on the charge, adds energy to it. And this is 1.5 volts here, this location in space. It enters the second battery and gets up to 3 volts, enters the third battery and gets up to 4.5 volts. So we've got 4.5 volt electric current showing up on this wire, going through that light bulb and leaving at almost no voltage. So that light bulb is experiencing a voltage drop of 4.5 volts approximately. The batteries are providing 4.5 volt rise, is a 4.5 volt drop, okay? And I told you that this light bulb was designed for essentially 4.5 volts to get just about as bright as it wants to get. It's not very bright, but that's what it gets when you put 4.5 volts across it, and it carries whatever current it normally carries at 4.5 volts. If I use less voltage, it will carry less current because you're not pushing as hard anymore. Electric field is weaker. And I can do that by just simply removing one of the batteries and tapping into the middle, in the middle. I'll do it with my fingers. So it's dimmer. It's dimmer because it's carrying less current because we're pushing less hard, and Ohm's Law says, and this is approximately following Ohm's Law, it's close. Since it's only got 2/3 of the voltage drop it used to, it's only carrying about 2/3 of the current. Moreover, that current isn't losing as much voltage as it used to because it's going from 3 volts to 0 instead of, it used to be 4.5 volts to 0. So it got dimmer by about a factor of 2 in some respects. It's consuming about half the power it used to. And if I keep going down to 1.5 volts, it's pretty wimpy. So this is sort of just a hand-wavy or a simple demonstration. The Ohm's Law idea is pretty good. That if you expose a conductor to larger and larger voltage gradients, voltage drops, it carries more and more current. All right? This incidentally is how your hairdryer gets to 1800 watts. It is designed so that when it's exposed to about 120 volts, it will carry about 15 amperes. And many of you have had the experience of taking your hairdryer or some other fashion item to Europe and getting a widget that will allow you to plug it into electric power in Europe. Electric power in Europe is not 120 volts anymore. It's more like 230, twice the voltage, give or take. So you've got twice the voltage. That means there's twice the electric field inside anything you plug in. So if you plug your hairdryer or your curling iron or whatever into European outlet, yes, you can mechanically do it with an adapter, but you've got a problem. You now have twice the push provided by that bigger voltage rise at the power company. It goes to your hairdryer or your curling iron, and now twice the current goes through it as before. Furthermore, that current is undergoing twice the voltage drop. So the power it consumes, which is the product of the voltage drop times the current, is 4 times what it's supposed to be. And you get about 1 second of life in the gadget before it goes up in smoke. It so overheats. It's complete death and destruction. And I won't ask you all to identify yourselves, but you know, on any given year, it's a whole bunch of students who have done this. You know, first experience at third year abroad. Don't do it. Don't plug in your, we now have an increasing number of electronic devices that manage to deal with the difference in voltage. Like a lot of your electronics will do that, handle this, your cell phone adapters and stuff like that. But the big power items like heating devices, hair dryers and curling irons and hair straighteners, they are not smart devices. They will just burn up. In short, they're ohmic devices. The word ohmic is simply a label applied to things that obey Ohm's law or pretty closely. And a hair dryer is pretty much an ohmic device. If you double the voltage across, the voltage drop in it, it will double the current it carries. All right? More stuff about circuits. I do have that turned up. Most circuits are designed to have, electric circuits are designed to have a power source and a power consumer. It is possible to mess up and to have a circuit that has a power source and no consumer, that is no designated consumer. And that happens, when that happens, you have a circuit that is sort of missing the equivalent of the light bulb. The light bulb is serving at least one purpose. It's limiting the current flowing in the circuit, for one, because it's an ohmic device that will only carry 7 amps when it's supplied with 12 volts. And it's also the obvious place for most of the energy, the power to be dissipated and to do something useful. The wires are participants in this. They are minor participants. They are consuming a little electric power, meaning that the current arrives at the red end of the battery, the positive end of the battery at 12 volts, and by the time it's worked its way through the switch, through the wires, back to the light bulb, it's not 12 volts anymore. These all are toll items. They all consumed a little bit of electric power. They're ohmic. The more current you send through them, the more they're going to charge for every passing unit of charge. Anyhow, they will have, the voltage will have gotten down to, I don't know, 11 point something, 11.5, let's say. And it's 11.5, and then it can't go all the way down to 0 by the time it leaves the light bulb, because then they won't have the payment, the energy to get back to the light bulb, to the battery. So the wires are present. They're consuming a little bit of electric power, but they're minor players. It is worth noting that the electric power that one of these wires consumes is not just proportional to how much current goes through it. How much does it consume? Well, when that light bulb is operating normally, it's carrying 7 amperes. That means this wire has to carry 7 amperes because charge is conserved. You can't have 7 amperes going through that without it passing through my fingers. Who would have made it or destroyed it midway? So 7 amperes going through this wire. This wire, to carry 7 amperes, needs a certain voltage drop, characteristic of the wire. That characteristic, incidentally, is the name for that characteristic of the wire is the electrical resistance of the wire. So this wire has a small but not 0 electrical resistance. You got to push to get the current to go through it. The light bulb filament has a big electrical resistance. You have to push very hard to get the current to go through it. So this guy's got a small but non-zero electrical resistance. And to get 7 amperes through it, it has to have a certain voltage drop across it. If you were to double the current you want to have go through this wire to 14 amps for some reason, you'd have to push twice as hard, and it would experience twice the voltage drop. The power wasted, consumed by this wire would go up by a factor of 4. So doubling the current in the power carrying wires, a takeaway, when you double the current going through power carrying wires, the electric power they consume, those wires, goes up by a factor of 4. It goes up as the square of the current. This matters a lot in modern life. I mean, you may not notice it, but the fact that the current starts to skyrocket, the power consumed by wires begins to skyrocket past a certain current because the power consumed goes as a square of the current, sets many of the limits on how much current you can realistically send through wires. And for example, house wiring, 15 or 20 amperes is about the most you want to send through. You will begin to violate various codes if you send more, because they will start to consume more and more electric power, and they will get hot and become dangerous. And that's certainly true of electrical extension cords. If you try to plug in your 1800 watt hair dryer into the world's wimpiest little extension cord that you got at the flea market, that cord it will charge a lot of voltage drop to carry your 15 amperes, and it will become a major consumer of electric power. It'll get hot and potentially start a fire. So this is why they don't want you mucking around with extension cords in your dorms. Be careful with extension cords, particularly cheap ones that are underrated, underpowered. You can overheat them by trying to coax too much current through them. Okay, so we're trying to make this a proper, complete story here. I was telling you the light bulb was the limiting factor on the current flow in this circuit. If I edit the light bulb out of the circuit and go directly from this wire to that wire, there's no official consumer of electric power left. It's just the wires. And they will limit the current eventually, because they are consumers. But that current won't be 7 amperes. It could be 50 amperes. The battery, actually, car batteries are potentially dangerous because they are able to deliver an incredible amount of current without they don't care. They'll go right up to several hundred amperes, happy. That's part of what makes them useful for starting cars, but it's also dangerous. It means that if you have a circuit with no consumer in it, the wires will get hot. And so here, I'm not going to just connect those wires together, because the wires will get hot and they'll all burn up, and I'm going to put in sort of a wire. It's a little bit of a worse conductor than the normal wires. Let me get this out of the way so it's not confusing. What I'm going to do is I'm going to add it around the existing light bulb. And it comes with a switch, so I can activate it. I'm going to turn the light bulb on. This is business as usual. However, I have a switch here that allows the current to skip the light bulb and go through that wire there and to the other side of the light bulb. Skip the light bulb. And I'll do it. Here we go. The light bulb dimmed a little bit because the current went way up in all these wires. And as a result, they consumed a larger fraction of the power than before, and the light bulb isn't getting the voltage drop it's used to. But that wire that we skipped, that's providing the extra path here, is red hot. And they get all stinky. So this is an example of a short circuit. So where am I going? It's a short circuit. The circuit basically is skipping, a good fraction of the current is skipping the light bulb and taking a shortcut. Let me turn it off before it gets too stinky in here. This is why you be careful with wiring, particularly, well, in any context, that you want to make sure that the wires, well, that you end up touching them. And that's for different reasons, because it's obviously hazardous to have electric current go through you. But you really want to make sure the current's following the right designated path with something that will limit the current flow and consume the electric power properly. All right? Questions? Okay, so some remaining things to talk about with circuits. Battery, how does the battery work? The way the battery works, so let me start with the simplest battery, a single cell. Batteries typically divide up into what are called cells. They're a chemical, or really electrochemical device where what is mobile inside the battery are positively charged molecular fragments, what are called positive ions. The word ion is a reference to a tiny particle typically an atom or a molecule, basically, that has a net charge. It's not electrically neutral. And they're familiar, they're everywhere. Ions are common. They come in both positive form and negative form. Some of the simplest ions I can think of, when you put salt in water, what's floating around in the water is little sodium positive ions and chlorine negative ions. How so? It turns out the chlorine atom is greedy for electrons, and the sodium atom sort of could care less about one of its electrons. And so when you put sodium and chlorine together, the chlorine naturally steals for chemical reasons. It steals an electron from the sodium. So sodium now is missing an electron, which means it's missing a negative charge. It's got one fundamental unit of positive charge. The chlorine, on the other hand, is one fundamental unit of negative charge. And they're happy like that. They float around all day. You've consumed tons of salt that way. So things like that are going on inside a chemical cell like this. It has ions in it. And it turns out that there are positive ions in this guy, and they have a preference for where they would be. If the positive ions can migrate from the side of the device that is labeled with a minus sign, if they can migrate by just random chance to some extent through the intervening material over to the positive terminal, they stick better there. The positive ions they're chemically attracted, bound to the positive end more strongly than they were at the negative end. So they do this. There's a statistical random walk aspect to this, but they eventually, when you first assemble this cell, it was all electrically neutral everywhere, although it had some little charged particles in it. There just were equal numbers at every location in space. And they quickly migrated so that you had an accumulation of positively charged guys on the positively labeled terminal and a slight deficit of them on the negative terminal. As a result, one end of the battery, the cell, is positively charged, and the other one is negatively charged. That continues to accumulate until eventually the positive charge repels further positive charges from showing up. So it reaches equilibrium, where there's a net abundance of positives on one side, net abundance of negatives on the other, and it's stable and it sits that way on the shelf for a long time. No charges are moving anymore. There's no net movement of charge because there's enough electrostatic repulsion to keep any further guys from moving. And in that situation, there's a voltage difference between the two sides. This is 1.5 volts above that, and that's just the way things are. If you now connect this in a circuit and allow electrons to leave the negative end, go through the circuit, and arrive at the positive end, you have neutralized some of that accumulated charge. And more positive charges can make the migration trip. It was at equilibrium before the electron made the trip around the circuit, and now you've spoiled the equilibrium. And as a result, the battery goes, wow, I can send some more positive charge to the positive terminal. This is good. And you then let more electrons flow around. And as you let more and more electrons flow around, more and more molecules make the positive ions make the trip from negative terminal to positive terminal. It's an ongoing, sustained adventure for the charges. So that's the basic idea of all these batteries. They differ chemically from one to the other, but the basic idea is the chemicals are chosen and designed such that positive ions like to leave the negative terminal through the chemistry and chemical soup to get to the positive terminal. They accumulate to a certain number and concentration limited by the chemistry. And at that point, there's a certain voltage drop across the cell. For alkaline cells, about 1.5 volts. For the lithium-ion cells, you're now awash in. It's a little above 3 volts, somewhere above 3 volts. And the charges sit on those terminals. You get positive charge and therefore positive voltage on the positive terminal, and negative charge and therefore negative voltage on the negative terminal. They're stable there until you let charge begin to move in an external circuit. And that charge is actually, the charge is moving in this case. It makes sense to look at it in close. It's actually negative charges, electrons, running through the wires to sort of undo the charging of the two ends of the battery and allow more charges to migrate through the battery. Questions about this? A little hand wavy. So with the switch open, there are positive charges accumulated on this, over here, negative charges accumulated over here. This actually has 6 separate lead acid cells in it. The chemistry, the lead acid chemistry is capable of developing a 2-volt voltage drop before the chemical conveyor belt shuts down, and it can't shove any more positive charges on the positive end. So you use 6 of them in series to make 12 volts. I was doing it over here with 3 of these 1.5 volt cells actually individually labeled to get to 4.5 volts. So their charges are sitting there. No more can migrate because they're being repelled by the accumulated positive charges on this surface. When I close the switch, I'm allowing electrons actually to go backwards through the circuit, backwards according to the language I've been using up until this point, and discharge the positive terminal a little bit so that more positive charges can go there. And the battery will sustain this all day. Eventually, it will run out of chemical potential energy. All of its positive ions will have made the trip, and it'll be out of stored energy, and the lights will go out. But that's what's going on inside the cells. All right? So, what about recharging a battery? Well, the battery in its normal mode moves positive charges onto the positive terminal to the extent it can. Once there are enough of them accumulated there to prevent further migration, the migration stops. But if you deliberately apply extra positive charges to the positive terminal from outside, you come up there with your positive charge source and you put it on the terminal, now the chemicals discover that they're in a weird situation. Not only is it unfavorable for the positive ions to migrate over to the positive terminal, it's actually favorable for them to go the other direction. And they go backward. They leave the positive terminal where they've been accumulating while you've been consuming power from the battery, and they go back to the negative terminal where they were back when the battery was manufactured. And you recharge the battery. So that's how you recharge batteries, is you run them backwards. And I can run them backwards here just for fun. These 3 batteries are arranged in the same orientation. This one has charge arrives here, charge being positive charge. Arrives here at low voltage, 0 volts. This battery increases the voltage to 1.5 volts. This battery takes it to 3 volts. It takes it to 4.5 volts. What if I reverse the last battery? So I take this battery out and put it in backwards. I don't know whether you can see it, but the light bulb is actually on. Really dim. What's happening now is charge is arriving here. There's again positive charge at 0 volts. The first battery pumps it up to 1.5 volts. The second battery takes it to 3 volts. And the third battery is backwards. We have a lot of positive charge here on the 3 volt one because the other 2 batteries packed it in there. So there's lots of positive charge on this wire. And this battery has that positive charge showing up at the positive terminal. And the positive terminal it's over the voltage it really had in mind. And the chemistry is running backwards. So positive ions, instead of going from low voltage to high voltage in this device, they're being forced to go backwards from high voltage to low voltage. And in doing that, the energy goes into driving the chemistry backwards. Current leaves the backwards battery back at 1.5 volts. This battery is basically subtracting 1.5 volts. And it's still got enough voltage to light the light bulb, but this battery is recharging. It's being run backwards. The main thing, that's the main thing. So when you're recharging your batteries, instead of drawing positive charge off the positive terminal and returning it to the negative terminal, you're doing the reverse. You're drawing charge off the negative terminal and shoving it against its will onto the positive terminal. and making the whole chemistry run backwards in the battery. And that concept has been around forever, and lead-acid batteries do a nice job with it. But most of the batteries, apart from lead-acid batteries, most of the batteries up until the modern era, modern being the past 20 years, 30 years, they didn't recharge well. And the reason for that is that, yes, you can run the chemistry backwards on basically any battery, but that doesn't mean that it reconstructs the original battery. Some of the original batteries had very fine, delicate structure in them, like powders, for example. And if the powder was sort of went away as a powder in consuming electric power from the battery, when you try to rebuild that powder, it doesn't rebuild as a powder, it rebuilds as a lump. And so the batteries didn't recharge properly. So apart from lead-acid batteries, which work very nicely, lead-acid batteries go from, there's almost no visible change in the components inside a lead-acid battery as it discharges. It looks like two plates in a soup, and the soup happens to be battery acid, which is mostly sulfuric acid. It's two plates in battery acid. They happen to be a little bit different, the plates, but it looks like that, and when you discharge it, it still looks like that, and when you recharge it, it looks like that again. So nothing much is happening. Lead-acid batteries keep working pretty nicely until eventually one of the plates breaks, which is the typical failure method for lead-acid batteries. Okay, but most of the other batteries, you could see they discharge by looking at them, and it didn't run backwards properly. So I grew up with batteries, nickel-cadmium batteries, nickel metal hydride batteries, which were better. Nickel-cadmium batteries are terrible. Nickel hydride, these are ones that are trying to be rechargeable. But now you guys are used to lithium-ion batteries, which recharge beautifully over and over and over again. The structures recreate perfectly, almost perfectly. There's almost no, the battery has almost nothing to tell you how many times it's driven its chemistry one way and driven back. So you're just like totally spoiled. Yeah, batteries used to be a real pain in the neck. Now they're kind of, all right. Anything else I wanted to convey along this? Questions about batteries, flashlights, light bulbs. One thing, before we finish, I do have one. In looking at the circuit, following the lead of basically most physicists and engineers, I talked about electric current, positive charge, the movement of positive charge. It goes through here, from high voltage to lower and lower and lower voltage, drops off most of its power in the light bulb, and returns at very low voltage to do the root again. If we look in detail to what the heck is going on inside these wires, it is not a movement of positive charge. Positive charge, the positive charge widgets in our universe are protons, the main ones. There are others, but protons are part of normal matter. They don't move, not in this environment. They do in the batteries because the batteries are there's more mobility, and they're not rigid solids anymore. So the positive ions can literally move, like in water. What's really moving in this wiring system is electrons, and they, alas, are going the other direction because they carry negative charge. Positive charge in our thinking is going around the loop, clockwise as viewed from above. It's really, secretly, it's electrons going counterclockwise around this loop as viewed from above. Electrons actually leave the negative terminal. They migrate through the wires, charging a fee as they go because they need to be pushed. They're actually moving. Electrons accelerate against the electric field. They're negatively charged, so the electric field says go that way in reference to positive charge. Electrons say, no, I'm going to go the opposite direction. So they're going backwards. They go through the light bulb. They emerge out of the light bulb at higher voltage, which is to say higher energy per charge, but they're negatively charged. So for them, it's the reverse, and they complete the circuit. Anyway, it's alas, a confusing pain to have to think that actually what's moving through the wires is electrons carrying negative charge going the other way from what we conventionally call current. People have learned to live with it. It is what it is. For the most part, we'll just watch current go and pretend it has nothing to do with electrons. Where it will become important is with electronics. Modern flashlights come in two types. One of them has a hot filament like this, where life is simple. And that filament doesn't care whether current flows through it from left to right or right to left. It gets hot either way. It charges a fee either way from the passing current and gets hot. The other modern flashlights are light-emitting diodes. And light-emitting diodes don't carry current in either direction. They're very picky, one direction only. And so we have to pay more attention to what's moving and in which direction. This is indifferent. All right, I'll stop and we'll go on with other things on Monday.